Hello students. Last time we studied about the pressure inside a fluid and we discussed two situations. When an imaginary cylinder was well dipped inside the fluid and when imaginary cylinder just touches the free surface of the fluid. Upper part of the imaginary cylinder just touches the free surface of the fluid and we got an expression for that. The pressure inside a fluid P2 equals to P1 plus Y1 minus Y2 rho G. This equation shows that if we go inside the fluid, pressure increases because this quantity, some positive quantity will add to the pressure P1 and you will get P2 which is the point which is below that comparison of P1. So pressure increases. Now today we are finding what will be the pressure above the free surface of the fluid. That is, as we are going above from the earth surface, what should be the pressure? So consider the situation here. The fluid is filled in the water of density rho. This is an imaginary cylinder. This bottom cross section area of the imaginary cylinder just touches with the free surface of the fluid, and this is the top surface which is at a distance d with this bottom surface, and we have to find out the pressure at this point, at the point y1 pressure. Let this pressure is p which is to be find out. Now again for reference we will consider this is positive y-axis is our reference line, this is 0, and now using the equation pressure inside a fluid, this equation will be used to find out the pressure. We only change is that we will substitute the quantities as per our diagram. So this is the equation P2 equals to P1 plus Y1 minus Y2 rho G. Here in this figure P2 is what? P2 equals to P0 because this point is Y2. So we call this corresponding pressure as P2. Right. So this P2 equals to P0. This point is Y1. Corresponding pressure we call it as P1. So here P1 equals to P. Density of air we will consider because the point is in air, not in the fluid. Here Y2, this point Y2 it is just touches to the reference line which is at 0. So Y2 equals to 0 and Y1 is in positive y-axis direction. So it will be D plus D. Then substituting these values in this equation, then it becomes P2 is P0. So P0 equals to, what is P1? P1 is P plus Y1. Y1 is D. Y2 is 0. Rho, you will consider rho density of air into G. So it will be P0 is equal to P plus, this is D, simply you will write. So this will be D G rho of air. So using this equation, we can find out the atmospheric pressure. Let it call as equation number 2. Now find out pressure at this point Y1. You write this on left hand side. So P equals to P0 minus dg rho air. This is equation number 3. Now see this equation carefully, and this is the equation inside the fluid. This equation number 3 is the pressure above the fluid surface at a distance t. Right? This P0 is the atmospheric pressure at sea level. Some positive quantity, this d is distance, it is positive. G is acceleration due to gravity is positive, rho is positive. So some positive quantity is subtracting from the P0. So this pressure P will be less than the P0. Right? So what we conclude, as we are going above from the free surface of the fluid, or so the pressure will decrease. Right? And as we are going inside the fluid, the pressure increases. So this is the conclusion. So pressure above the distance T in air or in medium will equal to P0 minus dg rho air. Only change is that you will consider here density of air only. Here we will considering density of the fluid because we are finding the pressure inside the fluid. So these are the situations. Okay. So you learn this concept and we will solve some sums based on it in the next lecture. Now we will see the concept of hydrostatic paradox. What is it? See this situation. These are three diagrams, three containers. These three containers of the different shape. One is the straight one, this is wider one, and this is the narrow one. In all the three containers, the same liquid is filled with the same height. So what is our common observation? That this wider container contains the more amount of liquid. So weight is more, maximum weight of the fluid is here than in the straight container, and the lowest weight of will exert here in the narrow container because the minimum amount of water or the liquid is occupied here. This is our general observation. As the weight is more, so force is more, force exerted at the bottom is more, and hence the pressure is more because pressure is equal to force upon area. So force is greatest here. So this is a general observation. Pressure is also greater as compared to this, and the minimum pressure will be in the middle diagram because of this particular shape. This is our general observation. But in practice, it doesn't happen. The pressure exerted at the bottom of this levels of the container is the same. If the containers are filled with the constant height, with the same height, same liquid is filled inside it with the same height, then pressure exerted at the bottom is also the same. And that is called the hydrostatic paradox. Now why this happens? See the diagram. In first diagram, the liquid is filled, then the pressure exerted or the force exerted at the bottom of the liquid is its weight. It also exerted at the sides of the container. So perpendicular force exerted in this direction and the bottom direction. So perpendicular force in one direction, as a reaction, walls of the container will also force as a reaction. So this is the reaction force of the wall of the container, and this is the reaction force of this wall of the container. They will cancel each other, and the pressure exerted by the weight of the fluid is only in the downward direction. In the second situation, what we observed, because of this shape, I am drawing this diagram over here. This type of shape is there for the proper understanding. This is the narrow one. So bottom will exert a normal force in the downward direction, or the weight of the liquid exert a force towards the bottom in downward direction. It's okay. But wall will exert the reaction force. This reaction force we split. See the force first. Perpendicular direction the force will exert. So this is the force in perpendicular direction. We split this force into two components. If this is the force, so this force F1 in horizontal direction and F2 in vertical direction. Same for here. Suppose this is the force exerted in perpendicular direction. It's split into two components. This is F1 in horizontal direction and F2 in vertical direction. See, this F1 will equal and opposite. They will cancel each other. This F2 in downward direction, they will add it, and as this diagram tells us that the weight is the minimum, so by addition of these two forces in downward direction, they will add the force and some amount of weight is balanced by this, and again pressure exerted will be the same as with respect to this diagram. In third case, see the diagram. In third case, this is the situation. this type of shape is there, right? So the bottom will exert a reaction force in the upward direction. Now here walls also exert a force, reaction force, in which direction? Perpendicular to the wall. So this is the direction perpendicular to the wall. This force will exert. Again this force will split into two components, one in horizontal direction and other in perpendicular direction. We call this as F1 and this is as F2. For second one, for second container, this is the force. This is splitting of the force in horizontal direction F1 and in perpendicular direction as F2. So this force, see this F1 will cancel each other, they are equal and opposite. These F2 they are adding up because they are parallel to one another, so they add up, and because of this addition of force in upward direction, some amount of weight will balance in upward direction, and as a result the pressure exerted at the bottom will be the same as with respect to this diagram, with respect to this diagram. See here no component is there, they will cancel, so the total weight in the downward direction is the weight acting in the downward direction. Here the weight is acting in downward direction if it is less, if it is seem to be less, but this component will add together, they will balance the amount of weight and the pressure will increase and it will equal to this. In this diagram the force will split up into two components such that the horizontal component will cancel each other, vertical component will add in upward direction, and the bottom will exert a force in downward direction. As a reaction, it exert a force in upward direction. So this upward part will add together and they will balance some amount of water. And hence this pressure exerted will be the same as this and will be the same as this. So this is called, these three diagrams are in the hydrostatic paradox. So if the same liquid is filled in the container of the different shape with the same height, then pressure exerted at the bottom of the surface are the same. So these are the hydrostatic paradox. Okay. In next lecture, we will solve some problems. Thank you.